Hi everyone, this is Professor Chen, and I'm going to give you a head up for this chapter, chapter 9, and that is about diffraction of beams. Diffraction of beams basically is to study the situation like this. So if we consider a beam, and that is, for example, this is under the cantilever clamped to the wall. And for example, here we consider a very simple loading case. For example, upon loading applied at the tip, the free tip here. So everyone knows under this loading situation, the beam going to deform like this, to deflect it, deform its shape like this one. So here, if we take the middle point as the measurement, so this is the diffractions at the free end, and this is we call the diffraction. So in these chapters, we're going to study how the beams are deformed vertically, and in particular, most of the applications we're interested in the maximum diffractions. For example, for this case, at the free tip here. And of course, the diffraction can be anything, can be anywhere as function of x. X basically here is our coordinate systems. So simply x can be anywhere across the beam. And this chapter is purely geometric, and the whole calculation will heavily depend on the solving differential equations. And how can I say that? And here is the very quick preview for you. For study the diffraction of the beam, we're going to review a little one piece of the equation we learned in bending. If you still remember, you can recall the bending have this equation here. And let me give you the more explanations. So for example, if we have the beam is under bending moment, and the beam has Young's modulus, E has a moment of inertia I here. The M is a given loading. So on the right-hand side here, this is the loading. The two are material and geometry informations. And from here, you can see the larger the bending we applied, the beam will be curved more. So this term here, this one representing is the curvature of the beam. The larger this value, meaning the beam being curved more. And on the other side, and you're going to learn from the very beginning of these chapters, you're going to learn based upon the pure, I would say, the calculus 1 or 2. The curvature can be described, approximate by d squared y dx squared. Okay, and we have the detailed introductions why this is doing so like this one. So therefore, from here you can see these are the given informations, including the loading, including geometry and material properties. This is the diffraction, the second order of differential equations of the y f x. Y is a diffraction here. We're going to learn. We're going to study. So basically here in these chapters, if we want to solve for the diffraction, actually here usually we're using y double prime. Basically in this chapter, you're going to learn, you're going to practice is how to solve for these simple ordinary differential equations. And usually to solve for this equation, let me move to here. These equations will come up with is you need, because this is second order differential equations, you need two boundary conditions. And the learning goal of these chapters is you have to place your attentions on how to identify appropriate boundary conditions and for you to solve for these equations. Okay. And I assume everyone should have learned how to solve for differential equations before you sign up for this class. So basically, again, you have learned, you have known how to solve for the equations here. But for the new things for you is how can you identify appropriate boundary conditions from the given loading to the certain type of the beam. And that is your focus here. And furthermore, in these chapters, and we're going to combine is a new piece of information is this one. We're going to combine is we know the dm dx equal to v, and also dv dx equal to minus omega of x. So that is a piece of the information we learned from the chapters of drawing shear and bending moment diagrams. And sometimes, depends on the situations, we might be able to combine the two equations together. Let me show you how to do it. So using these equations, then you can see basically that is, let me change the color here. So dm dx equal to vx. So from this equation, you can see basically is m equal to y double prime times ei. So therefore, combining this one, we take the one more derivative. So that means we combine the two things together. So we take one more derivative on m. So that means ei triple prime. So which means the third derivative of y equal to dm dx, and which is equal to v here. And again, by using this and these equations, we take the one more derivative of v, so that means dv dx, and what is v? We plug in the v here, so that is d dx ei y third derivative. So actually this one is equal to ei y to the fourth derivative here. Okay, so let me let you to see this one. So this one basically is equal to minus omega. So therefore, in summaries, another equation we might be able to pick up is this one, ei y fourth derivative equal to minus of x. And depends on the situation, that is the second portion you're going to learn in these chapters is how to apply this equation to solve for. And again, depends on the conditions of the loadings, and then that is the portion of the topics you're going to learn here. And one more time, for this equation, this is a fourth order differential equations, so you need 4 boundaries conditions here. So one more time, in these chapters, you're going to adopt is how to pick up appropriate boundary conditions for these equations, or the 4 boundary conditions for these equations. And for each equation, basically they are both equivalent, but you need to learn under which conditions picking up this is easier, under which condition picking up that one is easier. So that is the topics. And the final note is the superposition principle going to apply for. So which means if we have a different loading, so let me call this another loading called the F2, and this in addition to the original loading F1 here. So for this case, you can simply decompose the systems into a beam is under F2 plus a beam is under F1. Then you individually solve for deflection for this case, and for this case, you simply take summations together. One more time, the superposition principle applied to these chapters as long as everything is in elastic range. Okay, thank you.